Welcome to video 4. In this video we're going to investigate one of the biggest problems that we've seen in bucking coils that no one really has identified specifically, one that we saw in the last video but we didn't bring up except for the choking effect, is the fact that we couldn't really get the voltage up on the output coils or the output terminals over here. Now, remembering that we need a voltage because I equals V over R. So the voltage on these two terminals will determine the current that flows in the coils over here. So we need a reasonable voltage to power the load so that current can flow. And without the voltage, the current won't flow. Okay, so what we found in the last experiment was that our 12 turns here compared to our 45 turns, which is a 3.75 turn ratio, so we've got 3.75 more turns here on this half of the coil from this bit here all the way back to this bit here, wasn't enough to get the voltage up. Our voltage stalled, if you like. We couldn't get it any higher than what it was. For turn, for voltage, we couldn't get it any higher. Okay, and the reason that is because the coils over here, if you like, choke the current or the changing current on not only this coil but this coil as well. Okay, so we're finding that this coil over here is not able to carry any more current. Current is being choked off on this coil as well as this coil as well as this coil. Okay, the system is not able to find an equilibrium that is saying, okay, we're going to get the voltage up and then therefore we're going to carry a higher current. So we have a problem in the system. Our system is inherently not a generator yet, okay, and we need to think about how we're going to make it a generator. So again, the fundamental rules of electromagnetic induction would normally be a changing current induces a voltage. The voltage is what, in combination with resistance, is what determines the current out on the output. Okay, and remember again, there's nowhere in any of the equations that state that electromagnetic induction has anything to do with the output current. The output current is directly and specifically an Ohm's law equation which is dependent on the voltage and the resistance and not current. Okay, so I just want to reiterate those few points because in this video we're going to investigate how and what needs to be done to get the voltage up. Okay, so we've tried by reducing the turns, and effectively we've not got any more than what we've already had before. Okay, remember the 76 turns that we had up here, we reduced that down to 12 turns, which should have given us a step up factor of 3.75 to this bit of a coil here, and we didn't see it. We didn't see it because the current in the coils are being choked off. Okay. Alright, so we're going to do a quick test. Light is illuminated. We have a very simple setup. Okay, we have the same setup as before, so ends tied over here, so half of this coil here is up one way, back down the other way, so essentially the magnetic field cancels in this part of the coil. This part of the coil has all sorts of strange effects going on in it. Input coil again, and again the inductive part of the secondary coil over here, or secondary coils, partner output coils. Okay, so again, if you haven't followed the other videos, we have half of one coil inductive, half of that non-inductive because of this over here. Okay, so two coils, one and the one underneath, which is two partnered output coils. Okay, what I've done is I've put a measurement block on the cold side of the coil. Okay, and we have obviously negative to ground through our little resistor here, These things are fantastic, worth the weight in gold. If you haven't got one, build one. Very easy, very simple, very good. Same as before, switching via that channel. Okay, and this is what we've got on the scope. Alright, so looking at the scope as we are at the moment, we can see, trigger properly, we can see that the current here is being measured as 25% duty cycle. We started off with the frequency which we had in the last video. If you go back, was 2.4 kilohertz. So we're not really high frequency, but high enough to be not low frequency sort of thing. It's certainly not up around the radio frequency ranges or anything like that. But again, you can see 25% duty cycle in here. This is the current. Okay, so the current's ramping up a little bit. We're going to try and get a better trigger. And what we're going to do is we're going to expand it out a bit so we can sort of see it, wind the time across. Okay, now you can see in this part here, you can see that the coil's ramping up to here. And if you go back and have a read of our web pages, you will see that the effective change in current here, okay, because 5 time constants is 93 or 95.7%, whatever it is, I can't remember off the top of my head, but it's up around 93.7% of the entire waveform, the curvature there. So the curvature there is 5 time constants. So up to the top, up to almost peak current, which is the flat line. So that peak current, which is the flat line there, is 100%. The current that runs through the input coil is not going to increase anymore, it's not going to decrease anymore until we switch it off or do something else strange to the circuit. Alright, so you could say that our effective current, the change in current, remembering that we are looking at the change in current, is only that bit there. Alright, so the change in current where it's going to do something to the partnered output coils is only very, very, very small. And what we might do is we might actually wind that back a little bit and see if we can get a bit of an idea on roughly what frequency it might be. Alright, so we've wound it back a little bit. Let's see if we can get it triggering on the start so we can see it. There we go. Okay. So that is wound back a little bit, and that is actually, believe it or not, that's 10%. So we're looking at 10% duty cycle for 2.4 kilohertz. Okay, 10%. We're going to wind it back some more because we're still not at 93.7% or whatever it is. Okay, we're going to wind back a little bit more, a little bit more, a little bit more. Whoa, too far. Now remembering that these are going in 1% ranges. Okay, so we're about there. Now what we're seeing there is we're seeing the ramp up of current. Okay, so this is the change in current. Now I just want to explain, because we talked about rise over run. Okay, the run is the time, which is the x-axis. So if you look at the x-axis runs across this way. Okay, the rise is the y-axis. The y-axis runs up that way. Okay, so rise, which is that, over the run. So, or if you want to explain that even better, so the rise over the run. Okay, so we calculate the time it takes. We calculate the time that it takes for a coil to do what it needs to do by calculating the rise over the run. And we're pretty lucky here because we've got one time division. So we're pretty much a square box here. So we could say, because of that time division, which is 20 microseconds, okay, so we're looking at a very, very short pulse there, 20 microseconds for the run, and also 20 microseconds for the, I beg your pardon, no it's not, it's 2 volts for the rise. Okay, so the run is 20 microseconds and the rise is 2 volts. Alright, so we're looking at a rise over run, and that's what the input coil is doing. Okay, we're seeing a curve here, an exponential curve, and this is the magnetic field changing from 0, slowly changing all the way up to roughly about the 97 or 93% or whatever it is. That's 5 time constants is 93.7%. Roughly, and that figure, please go and look it up what 5 time constants are, because that's off the top of my head. I can't remember exactly what it is off the top of my head. It's been a while since I've dealt with it, but anyway, so that's what we're looking at. And if we wind it out even further, we can see we've got a lot of noise in there. We've got, if we turn down the okay, so now we're on 10 volts per division. We've got a big spike there. Okay, so we've got nearly 20 volts worth of spike, and this is as the current is being turned off. Okay, so it's a fair bit. Now, just remembering, we've got a probe on 10 times. Okay, so what we're measuring up here, the mean and the RMS, is the actual current that's actually along that. We've got the scope probe on 1, so remember 1 times 0.1 ohms times 10. Alright, and that's 1 ohm. So effectively the voltage that we measure across the resistor here, again we've covered this before, the voltage that we measure across that resistor is the amperes that's running through the circuit. Alright. Okay, so let's wind that time back down again, and we'll wind it back up so we can see. Okay, now we've got 2 time divisions, so we can actually see it better. It's a better view here. Okay, so I just want to reiterate. Now, most of you already know that will know this, but this is for the people that don't. So the exponential curve here, every time we see an exponential curve, we've got to think that at each point, that each dot that's been drawn on the screen is a change from the one beside it. Okay, and remember the change in magnetic field, which is the current. Okay, so as we have a changing current, we could say that the changing current is the same as a changing magnetic field, and that changing magnetic field is what creates a voltage in the secondary coil. So we can say that our effective change in magnetic field, if we wind it down and go back to the same time divisions that we had before, so we could say that the change in magnetic field is only 20 microseconds. Okay, the rise is only 2 volts. So we're getting 1 division, so it's 2 volts for this particular voltage rise, if you like, the exponential rise. 2 volts is the peak, okay, from 0, and that's the current. Okay, so you could say that this tiny little spike here, if you were just to measure just that over time and nothing else, forgetting everything else in time that's out over the side, the off time, if you were to measure just that, you could say that that's 2 amperes of current in that little box there. Okay, 2 amperes of current are being delivered to that coil in 20 microseconds. Alright, if my poor old brain is working and doing things right today. Alright, so the point of this, the reason why I wanted to go through it and try and explain this to the best of my ability, you can see the light is not as bright as what we had before, so we're getting a little bit less light. Because remember that we turned down the duty cycle. We went from a 25% duty cycle to now a 5% duty cycle. Okay. Okay, so I should explain, actually, to be honest, I should explain why, because some people may not actually realize. Now, remembering what I said, it's the change in current, which effectively is the change in magnetic field that creates a voltage. So the voltage that we're seeing over this globe at the moment, the voltage that we're seeing over this globe is a time weighted average of the entire current that's in the system. Okay, and what I want to sort of point out at this stage is we have less light at the moment for two reasons. First of all, the same voltage is there at the particular point in time when we're switching, so the voltage is the same, but the current's not the same. Okay, so what we've done on our input coil is we've wound our input coil back. So instead of having a 25% duty cycle, we've wound it back so that now it's a 5% duty cycle. So what we had before, with all that extra current that was running through the top here, that current was supporting the current on the secondary coil for a longer time frame. So that effectively what I'm trying to say here is the secondary coil was able to carry current for a longer time because our input was on for longer. I hope that sort of makes sense. Let's wind it back so we can, here we can see. So every part of this line when it's zero, what I'm trying to say, every part of this line when it's zero is a time that the secondary output coil is not being supported by a current in the system. So if our input was on for longer, then our secondary coil would carry current for longer. And the reason it would carry current for longer is because we are supporting that current from our input. Okay, it's got nothing to do with the voltage. The voltage itself has been generated in this part here. Okay, so the voltage itself in the system won't change, but the time weighted average through time that the current is being supported in the secondary coil is not as long. Okay, so we don't have current in the system for as long as what we had before, because as soon as we switch our input off, the output will ramp down the same as that, but in reverse. So if we go into our scope settings and we invert it, it's not the best way to view it. So you can imagine this would be the maximum current up here, and then the current would ramp down like this. It's probably not the best way to view it, but anyway. So maximum current up here, and then the current would ramp down to zero, which zero line would be down here, when the current is switched off. Okay, so you got to remember that there is a time that it takes for the current to ramp down as well. Okay, so I hope that sort of makes a bit of sense. Now going back to what I was trying to say before, is what we're going to do is we're going to do a quick test in the system and see if our load is going to make a difference. Okay, so to document, again, we have 20 microseconds. We have roughly 20 microseconds of time. Okay, and we have 2 volts roughly of peak. So from 0 to 2 volts is our x-axis. Okay, so what we're going to do is we're going to take that coil off. So we've taken it off the 2 coils over here. Okay, remember part of this is non-inductive, and what we've done is we've put it on this coil here. So that's the long coil. So this coil all the way underneath up to there is now carrying a current. Okay, and what we're doing is we're identifying in the system what it's going to take to get to the same settings that we had before. Okay, now we have a totally different effect. Okay, effectively one of the coils that was used before is still being used, but the input current that we're seeing in the system is now totally different. Okay, we're seeing nearly 2 time divisions there, and we're still not at peak current, and that's really interesting. There's a very good reason for that. Okay, well, let's try and find our 97.3% or 93.7% or whatever it is. Okay, we're going to have to wind this down, and we're still not there. Okay, you can see it's starting to taper off now, so we're not far away. And there you go, we're pretty flat at the top there now. Okay, so documenting, and this is important, we need to know what's going on. So we need to know in the system why the system's giving us what it is. So looking at the little things is really important. Okay, roughly, give or take, it's about at the point now where we can say it's about 93.7 time constants. And we have a totally different system. Now we have 50 microseconds from 20. Okay, we have 2 divisions being used up. So if we were even to say, right, well, let's go back the other way. Okay, so we're looking at roughly, in between here and here, we're looking at roughly 100 microseconds. And that's a huge difference. We're looking at a factor of how many? 5 times difference from 20 to 100. 2 volts, we're looking at almost double that now. So the current that's going into the primary coil, okay, to get to the 93.7%, whatever it is, for 5 time constants, remembering this is the change in magnetic field here, okay, that we're looking for. And we're looking at, let's use our cursors because that's always just so much easier, voltage. Okay, so from there to there we're looking at 3.52 volts. Okay, so nearly half a volt off 4 volts. So by going from non-inductive coils to a singular inductive coil, we have a totally different system, a totally different setup, and you can see specifically that before, because we were using non-inductive coils, we were seeing that the current was being choked off. There was too small of a time frame. The rise over run, the time frame was too small to really make much of a difference. Okay, just our non-inductive coils on the core, and remembering they were secondary coils, they're not primary coils, these are secondary coils, and just the way that they were connected completely changes the input to the system. So by the time we have our 5 time constants on our input coil, okay, by having output coils, partnered output coils that have different configuration, we completely change the way that the current flows in the system. Alright, we've not changed anything else. Input voltage is still exactly the same. Okay, input voltage 2.7 volts. We've not changed that at all, exactly the same. And we're measuring down here the current that is flowing through this primary coil here, exactly the same as in the other test. Okay, and all we're doing, the only difference is that we are using our 5 time constants as a gauge for how the system is behaving, for how the current is flowing through the system. So the input current flow through the system is completely different depending on how we have our coils set up. So if we look at the overall picture, okay, with bucking coils, if you like, if you want to call them bucking coils, with bucking coils there, the bucking coils completely change the way that the input coil accepts current into the coil and out of the coil again. The time frame, the rise, the run, the whole lot is completely different. Okay, for 5 time constants. If we're looking at 5 time constants, you can see now we've got more light on the light, but that's simply because the system has changed. Okay, we have a larger voltage on the coil, thus the light will light because there's more current flowing through the coil. And that's really what it's about. Okay, I've said it all along, we need to get our currents up, we need to get our voltages up. That is a given. Okay, you can't get currents up unless your voltages are up. You can't get your current up if the system is being choked off. Okay, so if our input coil can't put a magnetic field into the system that is able to do the changes, okay, so you've got to remember, if you like, say a magnetic field is say a bucket of water. If the bucket of water is only quarter full, then it's not going to make much of a change. If it's full, then it's going to make a big change. Okay, so we've got to remember that the system that we're working with, if it's choking off the magnetic field, which is what we are now seeing, okay, so it was choked off. 5 time constants was a completely different time and everything, so the input coil effectively was not really doing a very good job at getting a magnetic field into there. And remembering what we're looking for is the change. So we've got to look at these curves, and again, it's the area under the curve. So this curve is a change in magnetic field, okay, and it's the change in magnetic field that induces a voltage, and then when the voltage is produced, then a current can flow. Okay, we don't want the current flowing and stopping the magnetic field from doing anything before it can sort of really get to its peak value. We don't want to stop the system from doing what it needs to do. The system's got to do what it's got to do. We've got to make good use of the coils that we've got, and then as a result, once we have a magnetic field that's a reasonable value for as cheap as possible, then we can get a reasonable current flowing in the partnered output coils. And remember, it's the voltage that we've got to get first, and the peak here, peak of the current for this particular change, okay, remember, rise over run, and this rise over run is going to create a large magnetic field, and you can hear the difference probably in the background compared to before. So the magnetic field is much larger, and yes, it's going to cost us a little bit more, but what we've got to realize that this curve here is what gets the voltage up on the coils, and you can see big difference in light on the light for effectively the same frequency. We are back up to now, with this setup, we're back up to 24% duty cycle at 2.4 kilohertz. Okay, so I might keep this video short after the last video. I think at this stage, I think this is probably enough to start getting people to start thinking about this in a different way. I just want people to sort of, if they're interested, if people are interested and want to learn this, then I think it's important to look at the basics. We've got to look at the basics, learn the basics first. I mean, something like this, you would never be taught something like this in, at college or anything like that. This is something that you are probably not going to see in any textbook. You're probably not going to see in any physics class. You're probably not going to see generally across the board. Okay, so people really, to be honest, don't really know about this. I sort of lucked it just from doing what I'm doing. So moving forward from here, this is video 4. Moving forward from here, what we've learned is that the coils, it's very easy to choke the input magnetic field off. We want to get a maximum change in magnetic field from our input coil so that we can get the voltage up on the coils over here. We don't want the input coil to be choked off, to be starved, and not be able to get the voltage up on the coils. Remember the change in magnetic field over time, and that again over time, so that's the rise over the run. Okay, so the change in magnetic field over time is what we're looking for. That's what we're looking for to try and get the voltage up on the coils. So you can see there's nearly half half that spike there is effectively the difference that we've seen just in this experiment. Alright. Okay, so moving forward. So what we really want to do is we want to start thinking about a magnetic field and thinking about, right, well, our magnetic field needs to get the voltage up on the coils, but our coils need to stop, need to make sure that we don't reflect back on the primary in such a way as to choke it off. Okay, so what we probably need to do is we probably need to look at our structure, our coils, where they are placed. Okay, because remember we moved it from over here before to here. We dropped the turns. We were sort of expecting to see a voltage increase and we didn't see it, and now we know why. We know why we didn't see a voltage increase by dropping the turns, is because the partnered output coils, when they're in bucking mode, they starve the input coil off. Okay, so let's think about that. Let's think about where our coils are. Let's focus on how everybody has done it in the past, and try and move forward. The next video will contain a bit more information. Just want to thank everybody. The videos that I'm releasing at the moment, they are all basic introductory videos, videos that some with a much greater knowledge in electronics will already know. Most of this, perhaps not all of it. If this video has helped you, please consider a donation. This is what this is all about. We're all trying to do this together. So again, appreciate everybody. Thank you very much. Have a great day. Thanks.